Hey everyone, Mr. Fransky here. Today we're going to talk about sequences. Sequences are going to kind of dominate Chapter 9 especially, but we're also going to use them a little bit in Chapter 8. And I always call this middle school math because this is stuff that you learned a long time ago, but it's just going to be a little refresher of it first. So Chapter 8 has to do with sequences, L'Hopital, and improper integrals. So if you want to title your notes, you can do that. 8.1 is about sequences, just kind of a refresher on what they are. But before we do that, I want to do a little bit of integral review just because what happens is in chapters 7, 8, and 9, you kind of start to lose the idea of really rigorous integration because in chapter 6 we do so much with it and then we kind of lose it as you go through these chapters because we deal with simpler integrals, just a little bit of u sub here and there. So give these a shot if you'd like to. Really just more kind of think about how you would solve them. You don't have to work all the way through if you don't want to. I will. I'll just kind of do them quickly. But if you just kind of want to think through these before we move on, you're welcome to do that. So let's give these a shot together. So cotangent, the way I'm going to think about this, cotangent is not a well-known integral, but I'm going to think that's the integral of cosine x over sine x. Now I'm going to choose a u. I'm going to choose sine x because I can't get the sine x dx together. That's not a multiplication, but cosine x dx is. So du would be cosine x dx. That's right here. Right? Okay, so now I just have the integral of 1 over u du, which is ln absolute u plus c. I'm just going to put the u right back in there. So absolute sine x plus c. There we go. Okay. Next one on the left, that's a great candidate for a table. So I have my u and I have my dv. No line down the middle. I don't know why I made that. Okay, so the u is going to be x squared. And then that goes to 2x, and then to 2, and then to 0. We just finished down to 0. E to the x never changes. That's nice. And then we do positive, negative, positive. Okay, so we would have x squared e to the x, minus 2x e to the x, and then plus 2 e to the x, and then of course plus c. There we go. Okay, next one, also a great table candidate. It's a little bit more complicated, but it's still not too bad. So we have our u and our dv. U would be 3x, and then 3, and then nothing. Sine of x over 2. Now this is where we have to think about those constants, right? So the antiderivative of sine is negative cosine of x over 2. Now when we take the derivative of that, there'll be a 1/2 in front, so I have to throw a 2 out there to be ready for that 1/2. So I have negative 2 there. So the next one must be then negative 4 sine of x over 2. Okay, so positive and negative, just two things here. So we have, looks like negative 6x cosine x over 2. And then plus 12 sine x over 2 plus c. There we go. All right, this guy right here, that's a u sub. U is x cubed. Then du is 3x squared. We got the x squared. We need a 3 and a 1/3. So 3x squared dx is just 1/3 integral e to the u du. Antiderivative of e to the u is just e to the u, so this is 1/3 e to the x cubed plus c. There we go. Antiderivative of 7 to the x. A to the x gets people every time. Remember, the derivative you multiply by natural log of the base, so the antiderivative you divide by the natural log of the base. So over ln 7 plus c. Not ln x, right? It's not anything like with a power where it's like x 7 x to minus 1 or something. I don't know. I don't know how else you do it, but it's got to be 7 to the x over ln 7 plus c. All right, so that's a real quick little review of integrals. Now let's talk about sequences. So what is a sequence? In simplest terms, it's an ordered list of numbers. Ordered list of numbers. Whoops. Okay, so usually we use A for sequences, A1, A2, A3, A4. Okay, this can be finite or infinite, so I'm going to put an AN in there. So it could stop at the nth term, or it could keep going. This is called the first term. This would be like the third term. Okay, this is the nth term. Okay, and this could be finite or infinite, so it could stop or it could keep going. But the important thing is it's ordered, right? So like the first term might be 5, and the second term might be 6, and they're ordered. So they have to be in this order in order for them to be a sequence. But sequences are things that you guys have seen before. And we're going to start with kind of the simplest way, I think, to define a sequence is with an explicit formula. So you might have an explicit formula. AN is negative 1 to the n over n squared plus 1. So A1 would be negative 1 to the first divided by 1 squared plus 1. So negative 1 of the first is negative 1 divided by 2, so that's negative 1/2. A2 will be negative 1 squared, which is positive 1 over 2 squared plus 1, so that's 1/5. Looks like this is going to alternate every time, right? Alternating series are going to be, or sequences in series are going to be very important in chapter 9. So we have negative 1 cubed over 3 squared plus 1. That would be negative 1/10, right? Okay, and you could do this, keep going, right? Maybe we have like a sub 100. So a 100 would be negative 1 to the 100th power. That's going to be positive 1 because it's an even number, divided by 100 squared plus 1. So that would be 1 over 10,001, I believe. Okay, so this is kind of like a function. An explicit formula is one that has a formula like this. It tells you what the nth term is. This is like a function. So I'm going to write. So like a function. Because you can plug in any n term. Okay, you can plug in any n term, and it's going to tell you what that term of the sequence is. But it's not continuous, right? These are what we call discrete values. Okay, these are what we call discrete values because there's a first term, a second term. There is no like a 1.5, right? A function you think about like being able to plug in any decimal value, and you're going to be able to get a value out. But for these explicit formulas for sequences, you only use integers. Okay, so n is an element of the integers, or actually even the natural numbers. I'm going to say because we start at 1. We don't have like a 0th term. Okay, so n is an element of the natural numbers. 1, 2, 3, 4, 5, the counting numbers. Pretty the simple ones, right? Okay, so the other kind of way you can define a function or a sequence is by a recursive formula. So a recursive formula, for those of you who have taken computer science, is something that calls upon something that you've already done. So what we're going to do here is they give you the first term, and they might give you the third term or the 7th term. Just they have to give you some term, some starting point. Okay, so I always call this starting point. And then they tell you how to get to the next one using the previous one. So here, like A2 is going to be the previous term, A1, right, because that's 1 less than 2, plus 2. So A2, I already know A1, it's 4 plus 2, so it's going to be 6, right? And then A3 is going to be A2 plus 2, which is 6 plus 2, that's 8, right? What's the next one going to be? It's 10, then 12, then 14, right? We're adding 2 every time. So basically this gives you a place to start, and you can figure out what it's going to be each time by adding to the previous one. The problem with this is, what's A100? Well, according to our definition here, A100 is A99 plus 2. Well, what's A99? To get A99, you need A98, right? This is kind of annoying because you have to have the previous term to be able to get the current one. And you don't always have that, right? Like, sometimes you have to go all the way through all the terms to be able to get there. So now we're going to look at some typical types of sequences that are well known. Now we're going to look at an arithmetic and a geometric sequence. So an arithmetic sequence is one that starts at a spot and then you add a certain amount every time. So like the last one we looked at would be an arithmetic sequence, right? We add 2 every time. That's the common difference. So this one always starts with some term A1. And then you add that common difference. So, like, in our case, it was, I think, 6, and then 8. I don't know if it was 4. 4, 6, and then 8. But you add the difference every time. So first you add 1D, then you would add a second D. So A1 plus 2D. Whoops, erase. There we go. And then it'd be A1 plus 3D, and then A1 plus 4D. Doesn't look like a 3. There we go. That's a little better. Okay. Now let's notice what's going on here. So you have the first term. Let's write the nth term here. So the second term, third term, fourth term, fifth term. Notice that the number of D's you have is always 1 less than the term you're on, right? Because we haven't added any yet on the first term. So the nth term is going to be A1 plus n minus 1 times D. So that right there is the explicit formula for any arithmetic sequence. Explicit formula for any arithmetic sequence. So like if you know that the first term is like 18 and the common difference is, I don't know, 22, then your explicit formula, the nth term, is going to be your first term, 18, plus n minus 1 times 22, right? Because the first term, you're not going to have that 22 at all. But the second term, you'll have it once. The third term, you'll have it twice, etc., right? Common difference can also be negative, right? So you could have like, I don't know, 10, 7, 4, 1, negative 2, right? What's my common difference here? Come on. Way too far. What's my common difference here? It's -3, right? I'm going down 3 every time. So in that case, it would be 10 plus n minus 1 times -3. Okay? So if you have an arithmetic sequence, easy to come up with an explicit formula, and also really easy to come up with a recursive formula, right? It would just be an minus 1 plus d, right? That'd be your recursive every time. So let's look at some examples of this. Some of them are a little less obvious than others. So the first one, maybe we have -5, -2, 1, 4, 7. This is kind of the opposite of what I had before in the last one that I just made up. But in this case, our first term, let's write a recursive. So if you want to try that on your own, you can. Okay, so for a recursive for this, we just have to have the first term. Sometimes you see this little set builder over on the left here, like if it's a system, but you don't have to have it if you don't want to. So a1 would be -5, and my common difference is, looks like I'm adding 3 every time. So an is going to be the previous term, an minus 1, I'm going to be adding 3. Okay, so there's our recursive definition. If you want to write an explicit for this, the nth term is -5 plus n minus 1 times 3. Okay. All right, another example, and try to squeeze it over here. This is one, I love this example. It's one that doesn't look arithmetic initially, but let's take a closer look at it. So if we have natural log of 2, then we have natural log of 6, then we have natural log of 18, then natural log of 54, and let's say it's finite. Let's just say it stops there. So at first blush, it almost looks like you're multiplying every time, right? It looks like you're multiplying by 3, then by 3 again, then 3 again. But you have to think about how logs work, right? This is ln of 2, and then it's ln of 2 times 3, and then it's ln of, I'm going to write this as 2 times 3 times 3. Then it's going to be ln of 2 times 3 times 3 times 3, right? Okay, so we're multiplying by 3 one more time in the log, but remember log rules allow us to split this up to addition. So this is ln of 2, then it's ln of 2 plus ln of 3, then it's ln of 2 plus ln of 3 plus ln of 3 again. What am I adding every time? I'm adding ln of 3 each time. So this is a common difference of natural log 3, even though at first it looks very sneaky, right? So let's say we wanted to write, I don't know, maybe a explicit for this, right? So the nth term would be the, oh gosh, come on. The first term, which is natural log of 2, plus n minus 1 times natural log of 3. There you go. Okay, so a hiding arithmetic sequence. Okay, let's talk about geometric now. So geometric is where you have a common ratio, which means you're multiplying by the same thing every time. So you have your first term, a1, then you have a1, usually use r for this that you multiply by. Then you have a1 r squared, then you have a1 r cubed. So you're multiplying by this r every time. So what would the nth term be? It'd be the first term times, let's see, once again, first term, second term, third term. It looks like the power, once again, is 1 less every time. So it's going to be r to the n minus 1. Okay, so the nth term, just you've multiplied by the common ratio n minus 1 times at that point. So explicit formula, an is going to be equal to a1 times r to the n minus 1. That's our explicit. Recursive, excuse me. Recursive would be a1 is just whatever a1 is, so you write it in there. And the nth term, you take the previous one, n minus 1, and you multiply it by r. Okay. So, start with kind of a simple example of this. So let's say that you had 1, -2, 4, -8, 16. Let's say it goes on forever. So it looks like our first term here is 1, and our common ratio looks like we're multiplying by -2 every time. So an explicit for this guy, explicit for this would be 1 times our r, -2 to the n minus 1 would be our an. Okay. Another example, let's say we have, 3, 15, 75, 375, etc., etc. Let's write a recursive for that. So first term, a1 is 3. And then what am I multiplying by every time? Looks like I'm multiplying by 5 every time. So an is going to be the previous term, an minus 1, multiplied by 5. Okay? So nothing too fancy in these, not too bad. Let's talk a little bit about limits. So the limit exists of a sequence if, as n goes to infinity, the values are converging to a number. Okay, so if as n approaches infinity, an is approaching some number. Okay, now some people are quick to point out that arithmetic sequences then don't ever have a limit, right? Because if you add something every time, 1, 3, 5, 7, 9, right? These are just going to keep getting bigger and bigger. The only time that a limit of an arithmetic sequence exists if it's the same number every time. 4, 4, 4, 4, right? If you're adding nothing, like if your common difference is 0, then I guess your limit would be 4, right? They're more exciting though when something else happens. Like for this example, let's do a few of this. So the first term, be 2 minus 1 is 1 over 1. Which is 1. Then, when n is 2, you'd have 4 minus 1, which is 3 over 2, which is 1.5. Then you would have, let's see, plug in 3. 6 minus 1 is 5 over 4. Oh, I missed 3. What did I do? 3 times 2 is 6 minus 1, 5 over 3. 5 over 3, that's what I want. 5 over 3, which is 1.3 repeating. And then it looks like we can kind of see the pattern here, right? We're doing odd numbers, so it's going to be 7 over 4, which is 1.25. Then it's going to be 9 over 5, which is 1.2. Is that right? No, I did something wrong. Hold up. 9 over 5. I'm adding things wrong here. 5 over 3, 1.6, repeating. Mr. Fransky. All right, 7/4 is 1.75. This is much better. 9/5 is 1.8. What does it look like what's happening to these numbers? Oops, come back. Looks like these numbers are getting closer and closer to 2, which makes sense, because we know as n goes to infinity, the limit of this guy is going to approach those leading coefficients. This should be getting closer to 2. So this is what we're talking about with a limit. If you were to graph this, 1 is where we start, right? We're going to have dots. We're not going to have a continuous line. So 2, 3, 4. Okay, and we're going to be getting closer and closer to 2. So we're going to kind of approach that 2 value. They're never going to go above it, right? So epsilon kind of gets back into this. Remember from our limits when we talked about how you give me any tiny value. Let's say we're sticking with 2. Give me any tiny value. I'm going to go above and below that. So up here I have 2 plus epsilon. And down here I have 2 minus epsilon. So 1 is down here, right? We start outside of it, but eventually every single thing beyond is going to be able to fit into that epsilon neighborhood that you chose. So you give me a really tiny number, like 0.001. And I'll say, okay, as long as n is bigger than whatever value, let's say like 1,000,000, I'm going to say every n beyond 1,000,000 is going to give me a value that's within that 0.001 of 2. Okay, you don't have to know this, it's just kind of interesting. It's how real analysis defines this terms of limit of a sequence. It's not too bad. Okay, alright, I think I have a couple more examples, and we just want to talk about a little bit of vocabulary. So if this happens, we say it converges to a limit. The sequence converges to a limit. Okay, and if not, so otherwise, else, we say it diverges. Okay, so either it converges or diverges. I don't know why we're jumping around here. So let's take a look at some examples. So the first one we're going to look at is one we looked at before. 1, -2, I guess we didn't do this one. 4, -8. I think we did though, actually. Okay, so this sequence, the question is it convergent or divergent? I think you can see pretty quickly they're getting bigger, right? The numbers are getting bigger and they're bouncing positive, negative, positive, negative. But this is definitely divergent, right? Because we're not approaching any kind of a limit. How about -1 to the n? This one's kind of interesting. So this is an explicit formula. So an is -1 to the nth power. Now, some of you may have watched a number file about how the sum of all of the numbers from 1 to infinity add up to -1/12. It's an interesting number file, but they use this idea that this series, or this sequence, -1 to the nth power, that this converges. And in terms of the way we define it, it doesn't, right? Because if you were to do this, you would get -1 and then 1 and then -1 and then 1. It's going to go on forever, right? So if you were to graph that, here's -1, here's 1. It's going to look like this. So remember, the way we'd find this, you pick an epsilon. I don't know where you would put it. If you put it at up here, some of them are there, but every other term jumps out of your epsilon neighborhood, right? If you make this small enough, like smaller than, you couldn't have it all the way down here, right? But if you make it significantly small, like 0.1 or something, every other term is going to jump out of that neighborhood. Same if you try to put it down here, right? And it certainly doesn't make any sense to put it at 0. Like, you can't average it out because they never end up being close to 0. The way that Numberphile does is to say, well, let's just assume these all average out to 0. You can't do that. That's not allowed. Okay, not in terms of real analysis, anyway. So, let's see if I have one more. Yeah, cosine n over n. So there's another explicit formula. So as n goes to infinity, let's think what's happening here. Cosine n is going to bounce between -1 and 1. What's happening to the bottom, though? Bottom's getting really, really huge. And when that happens with fractions, the overall fraction is going to get small. So what's going to happen here is you're going to have something that looks like this. Okay, so eventually they get really, really close to 0. So if you choose an epsilon around 0, you can get far enough out that everything will be within there. So this guy converges to 0. Okay, so the sequence values here converge to 0. Now if you wanted to actually prove this, remember the sandwich theorem? -1 over n is less than or equal to cosine n over n less than or equal to 1 over n, right? Because the biggest cosine can be is 1, the smallest cosine can be is -1, so it's got to be sandwiched in there. Well, this turns into 0. This turns into 0. Therefore, this must also turn into 0 by sandwich theorem or squeeze theorem. So that's all you need to know about middle school math for today. I hope you learned something. Love you guys. That's why I'm here. I will see you in 8.2 for L'Hopital's rule.